So properties of exponents. So I'm kind of just going to give them to you, and then we will do some examples. We could get pretty deep into this stuff. Like there's a lot of really cool relationships that we can look at having to do with multiplication and addition and exponents. But in the interest of time, I want to make sure that we have time to do several examples at the end. So I'm going to kind of just go through the rules themselves fairly quickly, just so that we have them down, and then we can talk kind of about how to use them as we go through the examples. So just in general, exponential notation. If I have a to the n, that's a coefficient of 1, right, which is always there, even if it's not written, and then times n factors of a. So the key to kind of understanding the way that all of these rules work is that they all follow directly from the definition of exponential notation, or an exponent as repeated multiplication. And so we want to think of this exponent as a counter. So it just tells us how many factors there are. So it's not going to behave as a number in the sense that we're doing calculations with that itself, right? We don't actually ever do any calculations with the exponent, because the exponent doesn't actually contribute numerically to the expression, right? We're not multiplying by that number or adding that number or dividing by that number. All it's doing is telling us how many factors of a we're multiplying, right? So it's really like, I think of it as like an odometer, you know, like the little spinny thing that like counts up and up and up. So it's just a counter. So every time we get another factor of a, that's going to increase our counter by 1. If we divide by a factor of a, it's going to decrease our factor by 1. And so if we think of it that way, we get our first rule, which is the product rule. Which says that if I have n factors of a and I multiply by m factors of a, like how many factors of a am I going to have? Well, like I had n, and then I have m more, right?
Don't you just add them?
Yeah, because we start with n on our counter and we like count up m more times, right? So we wouldn't multiply the number of factors, because the things that are being multiplied are the a's. We're just the exponent is just counting how many times we're doing that, right? So like, for instance, if I have x squared times x to the third, I have 2 factors of x, and then I multiply by another 3 factors of x. And so altogether, I'm going to have 5 factors of x. So that counter is just increasing by 3 when we multiply by another 3 factors of x. And so if I have, let's see, here's an example, 4x to the 5th times 9x to the 4th. So one thing that can be a little bit tricky about the expressions that we're going to simplify in this section is that there's so many different ways of writing multiplication, right? So like we could put it in parentheses, we can put a dot between it. Sometimes we just smush 2 things together and call it multiplication. So it looks like we're multiplying 2 things here, but really we're just multiplying 4 separate factors, right? This is really like 4 times x to the 5th times 9 times x to the 4th. So we can rearrange those factors however we want. Like we can call this 4 times 9 times x to the 5th times x to the 4th. And we can do 4 times 9, yeah? Mm-hmm. So that's 36. And then how many factors of x is that? 9. Good. So x to the 9th. is our final answer. So, and it's probably worth mentioning that this is exactly the same problem. Again, there's a lot of ways we can make them look different without the operations actually being any different, right? Again, that's just multiplication all the way across. Especially when there's parentheses, people get really tempted to like distribute. But remember that the distributive property deals with multiplication and like addition or subtraction, right? So like if there's no addition or subtraction in the parentheses, then there's nothing to distribute to, right? It's just all a bunch of factors being multiplied. We just wrote it a different way. So you want to be on the lookout for that because we kind of fall into a pattern of seeing parentheses and like distributing things. But that only applies if there's addition, subtraction in those parentheses. So then we can, let's do the power rule. So if I have a to the n to the m, so here, let's do a simple one. This says I'm multiplying x, 3 factors of x to the 4th, right? So this is x to the 4th times x to the 4th times x to the 4th. So how many factors of x is that? It's going to be 12, right? Because if I use that product rule, I'm just adding 4 plus 4 plus 4. Which to me looks a lot like repeated addition. What's another word for repeated addition? Multiplication, yes. In fact, the relationship between multiplication and addition is identical to the relationship between exponents and multiplication, right? Exponents are repeated multiplication, and multiplication is repeated addition. And there's all sorts of cool like relationships as far as like comparing the different rules for each operation. But for our purposes right now, it suffices to say this is the same as 4 times 3, right? Adding 4 3 times is the same as multiplying 4 times 3. And so that gives us our power rule, which is that if we're raising an exponential expression to another exponent, all we have to do is multiply those exponents because it's like lining up m factors of a to the n and then adding all those exponents repeatedly. And I have a handout I'm going to give you at the end that summarizes all these rules, so you don't have to worry about finding them all when you're actually doing problems. So let's do, say, so we've talked about this negative business before, right? If I have negative 3 squared, what does that equal to? Right, so this is like negative 1 times 3 times 3, right? So that negative is like a factor of negative 1, and it's not part of the base of this expression. Like that's just 5 factors of x. And then I have this extra factor of negative 1. So it kind of becomes problematic because we have to separate those 2 factors because the 3 applies to both of them, but the 5 only applies to the x, right? And so the way we do that is just using this factor of negative 1. So anytime you see a negative sign, you want to think of it as a factor of negative 1. Dang it. Let me And so we're going to write this as negative 1 x to the 5th to the 3rd. So how many factors of negative 1 do I have here? Just 3. Good. Because this is like negative 1 x to the 5th times negative 1 x to the 5th times negative 1 x to the 5th. So if we count up those factors of negative 1, there's just 3 of them, which we write as negative 1 to the 3rd. put negative numbers in parentheses. Please, 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 for the love of all that is good and holy, put your negative numbers in parentheses. It's such a source of heartache if you forget the parentheses, because it changes the value, right? Just like we saw with that -3. So having a negative and then times 3 to the second is different than -3 raised to the second power, right? And so you're going to get wrong answers, and like it's kind of heartbreaking because they look so close to the right answer and you're just missing the parentheses. Like you have to put negative bases in parentheses every single time, or else it's all going to not work out correctly. So then we have how many factors of x? 15. Good. The 5th time that I remind you guys to put negative numbers in parentheses, there will be profanity involved. I'm just giving you fair warning ahead of time that I always have to cuss once. A colleague of mine and I always talk about this, like how like if we really want people to listen, like we have to like throw in like profanity every once in a while. So if it's really important, we just cuss, and then everybody's like, "Oh, I remember that time she said." But you know, I'll try it without 5 times, and then we'll see. So this leads us to what we call the power of a product rule. So notice that we started out with 2 factors in the parentheses there, and we essentially ended up applying that exponent of 3 to each one of those factors individually, right? We said, okay, that's 3 factors of -1 and 3 factors of x to the 5th. And so that's what the power of a product rule says. It says if you have a product raised to an exponent, you can apply that exponent to each one of the factors individually. So this is the same as raising a to the nth times b to the nth. So that kind of helps us get rid of parentheses in a similar way that the distributive property does when we work with multiplication and addition. So in fact, remember I said that multiplication and addition are related in the same way that multiplication and exponents are. So this is sort of like the distributive property of exponents over multiplication, whereas like the regular distributive property is multiplication over addition, right? So we can do that because exponents are repeated multiplication, so I could write it out all as multiplication and then move the factors around, right? Whereas if there was addition in there, that wouldn't work. If I had x plus 3 to the 4th, I can write this out as multiple factors of x plus 3. But because there's still addition in the parentheses, I still have 2 operations going on here, right? Up here, I wrote it all as multiplication, so we can start moving things around. Whereas down here, I still have multiplication between the individual factors, and the factors contain addition. And so there's no way to like start moving the x's and the 3's in such a way that I can group all the x's and group all the 3's, because there's still 2 operations. The only way to simplify that would be to just distribute like crazy, right? You have to multiply the first 2, then multiply that by the 3rd one, and multiply that by the 4th one. So there's no rules for exponents outside if there's addition inside or subtraction inside. It's only if what's inside those parentheses is multiplication that works. Does that make sense? Okay, so let's do a few examples with the multiplication rules, and then we'll talk division. maybe we will do 2. So there's not really like a set in stone order that you have to use the rules in. So all of these rules involve multiplication or division, which are all part of the same step in the order of operations. So there's not really like an order that you have to use the rules in. Sometimes it's more practical to use one rule and then the other. Sometimes it's easier to go a different route. But in general, it's always a good idea to get rid of parentheses first, because that allows us to work with all of the factors as opposed to like the factors over here and the factors over here separately. And so I'm going to apply those exponents to all of the factors in the parentheses first. So I have -3, which is in parentheses, to the 5th. Notice that factor of -3 is separate from the x squared, right? So we have to apply the exponent of 5 to it separately. And then we have how many factors of x? 10, good. And how about y? Good. And then we have 9 factors of 2, 27 factors of x, and 9 factors of y. And now we can kind of group these, right? Now that we got rid of those parentheses, we can say, okay, this is -3 to the 5th times 2 to the 9th. How many factors of x are there? Good. And y? Good. And like, we don't necessarily need those dots. I kind of just put them there for the heck of it.
Are we not supposed to do the multiplication if we can?
You should do that for me and tell me what you get. 112?
512.
Yeah, so that's pretty big, and these are really small numbers, right? As soon as that's a 5 instead of a 3, you get like a 5-digit number. Nobody wants that. And the point of all of this isn't what the number is, right? The point of all this is manipulating the exponents. I don't know why I wrote -37 there. That just came out of nowhere. I'm sorry. So there's absolutely no need. I mean, the only time, like, if I was going back to this problem right here, I would probably write this as -1 times x to the 15th, because -1 raised to any power is always either going to be +1 or -1. Like, it's never going to be a big, huge, insane number. But other numbers, they just get really big really fast, and there's no need. Like, it does absolutely nothing for us mathematically or in terms of learning to, like, put that in your calculator and write a big, huge, nasty number, right? Like, the point of all this is to manipulate the exponents. And in fact, if you do try to evaluate those and you do it too soon, you end up just making a mistake. And that's one of the biggest mistakes people make, is like trying to like get a number before you actually can. So if in general you don't actually evaluate it, then you'll never make a mistake because you tried to evaluate it too soon. So we just leave it like that. Nobody really cares what the number is until you're in a setting where it matters, and then you do it. So how about this one? We'll do 5 x squared to the 3rd x to the 4th squared. How many factors of 5 do I have? Just 1, right? Because it's not in the parentheses. Good. So a lot of this is just sort of recognizing like where things are and what factors the exponents apply to. So then this is 6 factors of x and 8 factors of x, which is how many factors of x? 14. Good. So let's talk about dividing. The quotient rule. Deals with dividing exponential expressions that have the same base. So if you think of writing a whole bunch of a's on the top and a whole bunch of a's on the bottom and then canceling a bunch of them, we're reducing the number of factors when we cancel, right? And so our counters are going to go down. So if I were to cancel m factors of a from the top and the bottom, I would end up with n minus m factors of a on the top, right? I've reduced the number of factors on top by m, and then 0 factors of a on the bottom, because I've also reduced the number of factors of m on the bottom by m. Or sorry, factors of a on the bottom by m. So for example, if I have x to the 5th over x squared, if I cancel 2 factors of x, I have 3 factors of x left on top and 0 factors of x left on bottom. What is x to the 0 power? 1, very good. So because it's 1 times no factors of x, right? So there's no way to get 0 from an exponential expression unless the base itself is 0, because we're not we have to multiply by a factor of 0 to get the number 0. And if I have 1 times a to the 0, there's not a factor of 0 anywhere in sight, right? I haven't multiplied by the number 0. There's just a 0 on my counter. Does that make sense? So anything raised to the 0 power is equal to 1, which means this is just a to the n minus m. Or down here, this is just x to the 3rd. So that's our rule. We skip this step. But it is worth noting that the result of that quotient rule is always in the numerator, right? So if we get a negative exponent, we'll see how to deal with that here in like 30 seconds. But when you actually do that subtraction, the result is always in the numerator. You don't want to like put it in the denominator prematurely. So we should talk about negative exponents. So if I have x squared divided by x to the 5th, well, now that we have the quotient rule, there's like 2 ways we can think about this. We can think of having 2 factors of x on top and 5 factors of x on the bottom, and canceling common factors. Which will give me what? Well, I mean, what I've written right there doesn't give me anything negative, right? So, but there is another way to do it, right? Now that we have the quotient rule, this should be equal to x raised to the, I keep writing 3, x raised to the 2 minus 5, like that's what the quotient rule says, right? Which is x to the negative 3. And so if we don't want everything we've done so far to fall apart, these 2 things have to be equal to each other. Equal, not equal. Have to be equal to each other, right? Because if they're not equal to each other, then the quotient rule is useless. It just doesn't work. So, and it makes sense if we think about it in terms of the definition of exponent. So the definition of like x to the 3rd is 1 times 3 factors of x, right? So if I have x to the negative 3rd, I want to do the opposite of multiplying by 3 factors of x, which is what? Dividing by 3 factors of x, right? Because division is the opposite of multiplication. And so instead, if I have x to the negative 3rd, instead of doing 1 times 3 factors of x, like I would with x to the positive 3rd, I'm going to do 1 divided by 3 factors of x, which gives me that 1 over x to the 3rd. So our negative exponent rule, the way it's usually stated is a little bit misleading. Oops, I didn't write negative. Negative. So if I have x to the negative n, that says take 1 and divide it by n factors of x. But really, it's just saying that that negative exponent means you're taking the reciprocal of x raised to the positive n, because we don't actually end up writing it like this in practice very often, because usually this is part of a bigger problem. So for instance, if I have 3x to the negative fifth, remember that x to the negative fifth means to divide by 5 factors of x. So what should that be equal to? So don't worry about the 1. So that's the thing that's misleading about this like rule, so to speak, is that every time we have a negative exponent, we're not necessarily going to see a 1 and then something in the denominator. If x to the negative fifth means to divide by 5 factors of x, and you start with 3, what do you end up with? 3 divided by x to the fifth, right? There is no 1 in sight, because it's, try not to like just copy the rule, right? Because then you're just going to have like 1 over this and 1 over that and 1 over this, and they're all over the place, and it's a big mess. You want to think of a negative exponent as just the reciprocal of the same thing with a positive exponent. So, or as division. So we have 3 divided by 5 factors of x gives us 3 over x to the fifth. You don't want 2 separate fractions. So similarly, if we have x to the negative third, y to the fourth, over x, no, we'll do a to the seventh, b to the negative fifth. So I definitely do not want like 1 over anything inside another fraction, right? That would be a big mess. So all that negative exponent means is to take the reciprocal, right? So if I have x to the negative third on top, then I want to divide by x to the positive third. Y to the fourth, I'm just multiplying by 4 factors of y, so that stays where it is. And then a to the seventh is just multiplying by 7 factors of a on the bottom. But then if I have b to the negative fifth, and I take the reciprocal, that's going to be up here. Right? No 1's in sight. So that negative exponent, it just really means take the reciprocal of that exponential expression and change the base to a positive. So you want to think of that negative sign as kind of a reciprocal sign or an opposite sign. So the opposite operation. And then that can't be simplified anymore because we don't have any factors with the same base. So those are essentially all of our rules. Let's do some examples. Let me give you this handout first. So 1, 2, 3, x to the third, y to the fourth. And that's a negative. Let me fix it. Times 2x to the negative fifth, y to the negative third, all to the fourth power. So for starters, we're just going to get rid of those parentheses. So we're going to apply the exponent of 2 to everything that's in that set of parentheses, and apply the exponent of 4 to everything in the right-hand set of parentheses. So we have 3 raised to the negative second, x to the what? Y to the 2 to the 4. X to what power? And y to the negative 12th. Good. So that took care of our parentheses. And then we want to look and see if there's a product or a quotient with the same base. So we have two expressions containing with bases of x. So what are we going to do with those exponents? Good. So I'm just going to put my numerical factors in front. Whoops, -2 times 2 to the 4th. And then we have x to the -26th and y to the what? -4th, good. And then from here, when it's time to take care of negative exponents, I always just draw like a big line, and then we're going to go through factor by factor. If we have a negative exponent, we're going to take the reciprocal. If we have a positive, it's going to stay where it is. So I have 3 to the -2, which is the same as dividing by 3 to the +2. 2 to the 4th has a positive exponent, and so it stays on the top. And then x to the -26th is the same as dividing by x to the +26th. And y to the -4th is the same as dividing by y to the +4th. And so now we've taken care of everything on our list, right? We don't have any parentheses, we don't have any factors with the same base, and we don't have any negative exponents, so we're done. Okay, you guys try this one. Nope, that's 2. X to the -5th. Y to the -3rd. This time we'll do 5 there, or a -5 there. Give that one a try. Don't forget what we talked about with the negative. Okay, what'd you guys write in your very first line?
The answer or just...
No, just the first line of your solution.
Okay, so the in parentheses -1 squared.
Oh, thank you.
Okay.
If anybody doesn't have that first thing written, change it right now immediately. In parentheses, Levi. No, the -1.
Okay.
So writing it once, like you have to write it in parentheses every single time. If you write it once and then it's not in parentheses for the rest of the time, then you changed its value in between. You know what I mean?
Okay.
Like if I write -1 to the second in parentheses and then my next line says this, then like these two things are different things. Right?
Yes.
They're different things. If you're not fully convinced that they're different things, this is something you should like convince yourself of, because it really for real is true. I promise. I'm not just making it up. Okay, carry on, Megan.
Okay, a to the 8th, a to the 6th.
I only pick on you because you're sitting right in front of me. I'm sure everybody else could be picked on just as easily. Carry on.
2 to the -5th.
Yep.
X to the 25th. Positive.
Yep.
And y to the 15th. Positive.
Everybody agree? Okay, somebody else tell me what they wrote next. Do you want me to call you by name? Because I could do that. Yeah, what's up?
-1 squared.
Yep.
In parentheses. A to the 8th, b to the 6th,
Yep.
x to the 25th, y to the 15th, all over 2 to the 5th.
25th. All these ended up positive. That's awesome. Over 2 to the 5th. Boom. Thank you. And we're done, right? Because none of those factors have the same base, which means we can't combine any of them, right? We have different variables for each of them. So all we could do is bring that 2 to the 5th down.
Amanda,
Yes.
can we write -1 squared as just 1?
Yes. So if you're going to evaluate anything numerically, it should be the very last thing you do. So if we could write this now as a to the 8th, b to the 6th, x to the...
Because it is 1.
Yeah, absolutely. That's the only one really that I do in general, is just if the base is -1, I'll write it as -1 or 1. Yes.
Would MML prefer like that way then, or if we put a -1 in there, would they call that 1?
I don't know that there's any like that in MML, but in general, they accept it in exponential form. It's sort of a special case when it's a -1. So like I usually will actually go that step with that one, whereas this one I won't, just because it's like either 1 or -1, and so it's not ever going to be a big number. If you type it like this and they don't accept it, just tell me and I'll just change the score, because that's perfectly fine. Okay, how about, let's do, ooh, this is a good one. X squared y to the -3rd over -6 z to the 7th. I feel like I'm writing too small to read that legibly. X squared y to the -3rd over -6 z to the 7th squared times x to the -5th y to the 4th over -3 to the -5th. Okay, give that one a shot. In the first step, when you get rid of parentheses, you can do one big fraction. Like you don't have to do those as two separate fractions. Like you could do one big fraction and put everything from the first one that's on top, and everything from the second one that's on top. So that, like, so you're not doing two separate ones. Like, go like this. Be like x to the, or x squared to the second, and just go across the top. And that way you don't have to try to think of it as two separate things. Okay, here we go. So like I said, like you can do just kind of like one big fraction. And then we have x to the 4th, y to the -6th. Then on the bottom, -6 squared, and z to the 14th. And then just keep going with the next one. So x to the +25th, y to the -20th, and on the bottom, -3 to the -5th. And then at this point, you sort of have choices. Like you could, if you want to take care of all your negative exponents here, you could. I usually combine the factors that have the same base next, just because I don't know if I'm going to end up with a negative or positive exponent. And if you deal with the negative exponents now, then like subtract and get another negative exponent, then you have to like do it again. So I'm just going to put them together at this point. So on the top, I have x to the 4th times x to the 25th, which is x to the 29th. And then y to the -6 times y to the -20th is y to the -26th. And then that's all there is to that. And so now all that's left is taking care of negative exponents. So again, we're going to just go through factor by factor. X to the 29th has a positive exponent. Y to the negative 26th has a negative exponent, so it's going to come down here. Negative 6 squared has a positive exponent. You don't have to put it in the front, but it's sort of just convention to put the numerical factors in front. Z to the 14th has a positive exponent. And then that negative 3 to the negative 5th has a negative exponent. So it comes up top. So keep in mind, like those negative exponents, it's not that they're always on the bottom, it's that they switch sides, right? So if you have a negative exponent on the bottom, it becomes a positive on top. If you have a negative exponent on top, it becomes a positive on the bottom. And also notice that these negative signs have nothing to do with whether or not we're on the top or the bottom. That's just part of the base. It's only the negative exponent that will make something take the reciprocal. And so that would be our final answer. Questions? You guys did pretty good. I only caught a couple of you without parentheses. Hopefully your homework tomorrow will be just as good with respect